Hello, hello. How's everyone? Um, so, I mean, the goal of this stream is pretty simple. We're just gonna relax and do some math problems. I have some music on in the background. Please let me know if it's too loud or anything like that. But the problem I wanted to start with is this one. And just for some context, I've been doing more and more kind of competitive math stuff recently. A big reason for this is that, for anyone hopping into the stream, it's pretty easy for them to follow what's going on. Whereas if I'm doing like calculus or linear algebra or something, there's a chance that they might not know what's going on. So let's get started. How might you solve a problem like this? Well, to get started, you might want to consider, I guess there's like a slow way to do it and like a fast way to do it. So let's try and think about what the perhaps slower way to do it is if you don't know anything better. So for example, you could try to cube both sides of this equation. And if you tried to cube both sides of this equation, you would get, you'd have like r to the 1/3 plus r to the negative 1/3 cubed equals 3 cubed, which is 27. Now, you would have to remember that, for example, if you wanted to do a plus b quantity cubed, then this would equal a cubed plus 3a squared b plus 3, ab squared plus b cubed, right? And applying this here would tell you that r to the 1/3 plus r to the negative 1/3. Let's see, hold on, I don't like this song. That one's okay. So, hey Mohammed, how are you? So I'm just going over how you might solve this problem slowly if you had no idea what to do. Also, please let me know if the music is too loud and if the audio quality is good and so on. So it's r to the 1/3 plus r to the negative 1/3 cubed we're doing. And of course, remember, a plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, right? So if you cube this, you would get like r plus r to the negative 1 plus, it would be 3r to the 2/3 times r to the negative 1/3, which would just be 3r to the 1/3 plus 3r to the 1/3 times r to the negative 1/3 squared, right? So this would be 3r to the negative 1/3, right? Which is equal to 27. But then you would have to notice that, for example, r to the 1/3 plus r to the negative 1/3 is the expression that you start with. And so you would have like r plus r to the negative 1 plus, I guess, 9 would equal 27. So you'd get r plus r to the negative 1 equals, I guess, 18, right? And then you could try cubing this again and recursively solve the problem. So for example, if you cube this again, you would get r cubed plus r to the negative 3, which is good news because those are expressions that occur above, right? Plus, I guess, 3 times r squared times r to the negative 1, which is just 3r, plus 3 times r to the negative 2, which is just 3r to the negative 1, which is, I guess, equal to 18 cubed, right? And so, once again, r plus r to the negative 1 we know is 18, right? If I'm not mistaken. So this basically says that r cubed plus r to the negative 3 plus 3r plus r inverse, which we know is 18, is equal to 18 cubed. So I guess the final answer would be basically r cubed plus r to the negative 3 equals essentially 18 cubed minus 18 times 3, which I believe is 54. Okay? Hopefully that makes sense, and that solves the problem. Of course, I mentioned this because there is a faster way to solve this problem, okay? Which I kind of want to get into. So just so you know the source that I'm using to get these problems, it's a book called Mathematical Olympiad Treasures by Titu Andrescu and Bogdan Enescu. I don't know where these people are from, but I think they're like mathematical Olympiad legends or something like that. You can see that this is the source that I'm using to get these problems. Okay. What is a faster way to tackle this problem? And essentially the method that I'm going to talk about is going to apply to essentially all of the problems that we're going to discuss today. Okay, hold on, I don't like this song. Let's try that. No, we'll see how this song goes. So usually they teach you a good number of factorizations when you first start out learning things, right? They teach you a good number of factorizations. So for example, the factorization that you probably use most often is this one. So, you know, a squared minus b squared equals a plus b times a minus b, right? I'm sure you've used this one a million times, right? Of course, you can take this a bit further and, for example, a cubed minus b cubed is going to equal, you know, I guess a minus b times a squared plus ab plus b squared. You usually learn these factorizations in, you know, like I think algebra 1 or something like that, you know, in like middle school before you enter high school. There are other interesting factorizations as well. So for example, one of my favorite types of problems that you can solve via a tricky factorization is something like this. So for example, let's say m and n are integers, and m times n plus m plus n is equal to, I don't know, 6. How would you solve this problem? Let me know if there are any ideas here. So m times n plus n equals 6. How might you solve this problem? So this problem is very common. I think it appears in a lot of like fancy like middle school exams or whatever. And there's actually a very like sneaky way that you can use to kind of solve this problem. And well, here's what you can do. Just add 1 to both sides of this equation, right? So you would have m times n plus 1 is equal to 7, okay? But then m times n plus 1, I believe, is just m plus 1 times n plus 1, which is equal to 7. But I said m and n are integers, which means m plus 1 and n plus 1 are integers, and their product is equal to 7, which basically forces that m plus 1, you know, is either 1... Ugh, don't like this song. I got like a new royalty-free music library to use. I'm just testing it out to see if the songs are any good. So this basically tells you that either m plus 1 is 1 and n plus 1 is 7, or possibly that m plus 1 is 7 and n plus 1 is 1, or possibly the m plus 1 is a negative 7, n plus 1 is a negative 1, or, you know, m plus 1 is negative 1, n plus 1 is negative 7, and you can just solve these. Yeah. So when I was in, like, when I was younger, this used to be my most favorite factorization trick. Like, I really loved this particular factorization trick. It kind of stuck with me. It always made me happy every time I got a chance to use it. Of course, there are more interesting and rather curious factorization tricks, and I'm going to teach you one today, basically. So I'm curious if anyone in the chat knows how to factor the following expression. A cubed plus b cubed plus c cubed minus 3abc. Let me know. If no one has anything to say, I will soon enough tell you how to do it, because it's a very interesting factorization. And you can think about it in a number of different ways. So there are a couple of different ways to write the factorization of this, all of which are actually quite useful in solving kind of tricky problems. So has anyone seen a factorization of this expression before? It's actually quite interesting. Please take your time. Let me know if you've seen a factorization of this expression, essentially. Well, here's something interesting. You can factorize this expression by looking at a determinant, actually. There are actually a number of different ways to figure out how you can factorize this expression. So let me tell you like 2 different ways you can use. I think these terms show up in a plus b plus c quantity squared. You know, you're closer than you might think, Mohammed, but that's not exactly right. Here, let me show you something. So there's a couple of different ways to figure out how you can factorize this expression. And but once you have it, you can use it to generate a lot of kind of sneaky problems that you can use to harass like high school students with. So for example, one way you can think about how to factorize this is you can think about the determinant of the following matrix. You just do ABC, like A, B, C, A, B, and then A. Hold on. So I'm going around. So this would become B, C, A. Okay. What would the determinant of this matrix be? Well, if you're interested in the determinant of this matrix, well, you can just use the formula. You can develop by the first column or whatever. In which case, you'll notice that the determinant of this matrix is exactly a cubed plus b cubed plus c cubed minus 3abc. Okay? And that's fantastic. But notice you can, for example, add all of the columns to the first column, and that's not going to change the determinant of this matrix, right? So for example, the determinant of this matrix should be the same as the determinant of the following matrix. So you have a plus b plus c, and again, a plus b plus c, and again, a plus b plus c. So this is what happens if you add both of the side columns to the first column. And then here you have BAC, and here you have C, B, A. Okay, so let me clear up the screen just a little bit. So, can move this over. Okay, but if you remember the properties of determinants, and don't worry if you don't know anything about determinants, I'll factorize this in a different way without using determinants later. But the determinant of this should equal a plus b plus c, because remember, determinants are multilinear, so if you take the multiple of any column, right, you should be able to factor it out, times 1bc, like the determinant of 1bc, 1ab, and 1ca, right? And now, what's the determinant of this one going to be? Well, you can check very quickly that the determinant of this is just going to be a squared, right? It's going to be like a squared minus bc, b squared minus ac, and c squared minus ba. So if you clear this out, you get very quickly that this is just, you know, a squared plus b squared plus c squared, right? Minus kind of all the pairwise terms. So ab minus bc minus ca. Okay, so this is why I said, Mohammed, like you do have something kind of similar here, but not quite 100%. Now this factorization is actually very, very powerful when it comes to generating kind of trick problems. Okay, so let me write this factorization in a slightly different way, and then we're going to use it to solve a bunch of like trick Olympiad style problems that often show up. So let's see. You know, you have this, right? You can actually rewrite this in a more kind of pleasant way, because a squared plus b squared plus c squared minus ab minus bc minus ca, you can just think of as 1/2 times, it would be like a minus b squared plus b minus a squared plus c minus a squared quantity. So this is another way to write this factorization, and this one's even more interesting because, for example, if you stare at this for long enough, you can get a proof of the AMGM inequality in 3 terms using this, which is nice. Okay, so you have this. This is one way to write the factorization. Okay, and then there's actually another way to write this factorization, which is also interesting. But first of all, let me prove the factorization to you in another way that does not use determinants. So this is our factorization. We have, or at least we've justified in one way, that a cubed plus b cubed plus c cubed minus 3abc is in fact equal to a plus b plus c times, there's a number of different ways to write it, but one way to write it would be times 1/2 times a minus b quantity squared plus b minus c quantity squared plus c minus a quantity squared. A rather lovely, I would say, a very beautiful factorization, I would say. I like this one a lot. So is there another way to factorize this? Well, yes, actually. Well, first of all, let me justify it differently. So another way that you can use to kind of justify this particular factorization, or like another methodology that you can use to basically prove this factorization, is by looking at certain polynomials. So for example, if you look at the following, look at a polynomial, look at a cubic polynomial that has roots a, b, and c, right? So consider a cubic, okay? Consider a cubic with roots a, b, c, right? Let's consider a monic cubic with roots a, b, c. So I'm going to call this a cubic polynomial, say like f of x, okay? Then of course, f of x is going to be, right, x minus a times x minus b times x minus c. Agreed? So if you multiply all of these out, notice what you get. You would get x cubed minus a plus b plus c times x, right? Plus ab plus bc plus ca times x squared minus abc, right? So this is what f of x is going to equal to. I'm just going to write it up top. So this is going to be the cubic polynomial that has, the aforementioned roots, that has the roots that we want or need. Okay, so far so good. Let me know if there are any questions at all about anything that I've done so far. So this cubic polynomial has roots a, b, c. So f of a is 0, and f of b is 0, and f of c is 0. So you get the following three identities. So f of a being 0 basically tells you that a cubed minus a plus b plus c, a plus ab plus bc plus ca times a squared minus abc is 0. Similarly, f of b being 0 tells you that b cubed minus a plus b plus c times b plus, ab plus bc plus ca times b squared minus abc is also equal to 0, right? And then f of c being 0, of course, tells you that c cubed minus a plus b plus c times c plus, of course, ab plus bc plus ca times c squared minus abc, right, equals 0. So what does this tell you? Oh, this is very simple now. You can just add these three inequalities. I'm not inequalities, sorry. You can add these three equalities and let's see, or these three equations. Let me just clear up some room a little bit. So if you add the three equations that you get by staring at these, right? For example, you would get that, for example, a cubed plus b cubed plus c cubed minus 3abc, right? And then minus a plus b plus c, right? Times, it would be a squared plus b squared plus c squared. Oh, I messed up. These should be squared, and these should not be squared. These should be squared. And these should not be squared. My bad on that front. Sorry about that. Let me know if that confused anyone. But assuming that that's okay, so this is going to be a squared plus b squared plus c squared, right? And then another plus a plus b plus c, right? Times ab plus bc plus ca is equal to 0, which again gives you the exact same factorization, okay? Which is kind of neat. So you have a cubed plus b cubed plus c cubed minus 3abc minus all of this is equal to 0. And of course, this gives you a cubed plus b cubed plus c cubed, right? Minus 3abc is again equal to, of course, a plus b plus c times, again, a squared plus b squared plus c squared minus ab minus bc minus ca. Okay? So now we've justified this factorization in two different ways, one using determinants and one without using determinants. Okay? So we've justified this factorization in two different ways. So I would like to use this factorization to solve some tricky problems. Nice. So Mohammed says, nice. Like, how do they even think to look at the roots of a cubic polynomial for factoring? I think this identity has been around for like hundreds of years. I think people used to just sit in their rooms playing with polynomials. No lie. There's so many interesting identities involving polynomials. So I'm not done yet because there's another way to write this factorization. So I swear I'll be getting to some interesting Olympiad style problems very, very soon. And we'll be solving this problem very, very soon using the trick that I've just... Actually, you know what? Why don't I solve this problem first, and then I'll get to a different way to write the same factorization. Also, this song is kind of a little too mellow for me. All right, maybe this one's better. Okay, so how are you going to do this? Well, here's one interesting implication of the factorization that I showed you. So the factorization that I showed you is that, you know, if a cubed plus b cubed plus c cubed minus 3abc is equal to a plus b plus c times some stuff, right? So in particular, this is telling me that if a plus b plus c is 0, then a cubed plus b cubed plus c cubed is always going to equal 3abc, which is a very, very interesting identity. I don't know, that's kind of amazing when I first saw it. So in fact, if a plus b plus c is 0, right, you'll automatically get that a cubed plus b cubed plus c cubed is going to equal 3abc. I mean, come on, who saw that one coming? I certainly didn't. It's lovely. It's a lovely little identity. Okay, so now we can use that here and solve this problem very quickly. So for example, we have here that, you know, r to the 1/3 plus r to the negative 1/3, right? Minus 3 is 0, right? Which means the sum of their cubes is going to be equal 3abc. So it's going to be, so this is going to tell you r plus r to the negative 1, right? Minus 27 is going to equal negative 9, right? Which immediately tells me that this is going to equal 18. So notice how much faster this is than what I was doing before, right? But now you know that r, actually, I don't know why I wrote it this way. I could have written it faster this way. So minus 18 is 0, right? But now the fact that these add to 0 means, again, that their cubes will add to 3abc. So their cubes will give you r cubed plus r to the negative 3 minus 18 cubed is going to equal 3 times 18. And now we're done. How nice is that? And you can imagine if you're like a math Olympiad problem designer or something like that, you could really make someone suffer. Like you could, if the year is let's see, what's a year that's divisible by 3? I don't know, 2025. You know, you would definitely do something like, tell me what r to the 2025 plus 1 over r to the 2025 is, or something like that. You know how they think. They always use the year in those problems. So But you can solve for something like that by just repeating this particular thing over and over again. And this is really good. This is very fast. So you have this, okay? Now, before I move on to another problem, before I move on to another like interesting set of shenanigans that you can engage in using this identity, let me show you another way to factor this, which is also, I think, extremely beautiful. So we've already discussed how to factor this quantity, right? It's a cubed plus b cubed plus c cubed minus 3abc, right, is going to equal a plus b plus c times some stuff, right? So this is going to equal, you know, a squared plus b squared plus c squared minus ab minus bc minus ca, right? Here's a question. Can we factor this one further? Can we factor this piece further? And maybe, kind of, yes. So if you're willing to use complex numbers, you absolutely can, okay? So watch me now. What I'm going to do is I'm going to treat this as a quadratic in A, okay? So just pretend that A is a variable and B and C are kind of, just pretend A is a variable and B and C are constants, okay? So we're examining this particular quadratic. So this is a squared plus b squared plus c squared minus ab minus bc minus ca, okay? So this is a quadratic in A. So what would the roots of this quadratic be? Well, the roots of this, so for example, this is the squared term, this is the linear term. Actually, hold on, let me write it very well so that it's clear. So if we think of this as a quadratic in A, you can rewrite this as a squared, right, minus b plus c times a, right? And then plus b squared plus c squared minus bc, I guess. That seems reasonable. So this is how you would rewrite it if you were thinking of this as a quadratic in terms of A, okay? So this is how you'd write this if you were thinking of this as a quadratic in terms of A. Now we can use the quadratic formula to get the roots of this, okay? So what are the roots of this going to be? So negative b, so this is b plus c, right? Plus or minus the square root of b squared, so that's b plus c squared, which is interesting because this is going to become b squared plus 2bc plus c squared minus 4ac. So this is going to be minus 4 times, well, b squared plus c squared minus bc. Okay, I swear this is going somewhere. I swear this is going somewhere pretty, even though it looks kind of like a mess. But let me just make a little bit more room for myself over here. Okay, so this is the thing we're examining, and this is what we are looking at. Okay, so you might notice that this thing, over 2, right? This is going to be the roots of this equation. All right. So now you can subtract some stuff off, and so inside here, if you stare at the discriminant for a second, this is going to be b squared minus 4b squared, which is going to be negative 3b squared. 2bc plus 4bc is going to be 6bc. Once again, I'm looking underneath the square root. And then c squared minus 4c squared is going to equal minus 3c squared. Aha! So this is actually equal to, negative 3 times b minus c quantity squared. You see that? Okay, hopefully that makes sense. Okay, we're cooking. So you can just put this inside here, right? Haha. All right, you just put this inside there. Okay, my selection is too big. Okay. All right, just put this inside there, which is really nice. So you can get rid of the squared part, right? So this is going to be b minus c, and, well, I, right? So I square root of 3. This is going to be I square root of 3. which, let me rewrite this, okay? Let me split this into its two constituent roots. So what are the roots of this polynomial? The roots of this polynomial are sort of b times 1 plus I root 3 over 2 plus c times I minus I root 3 over 2. Okay, that's one root, right? What is the other root of this polynomial going to be? Hold on, let me just make a little bit more room for myself. And the other root of this polynomial is going to be just b 1 minus I root 3 over 2 plus c 1 plus I root 3 over 2. Okay, so anyone recognize these numbers? These numbers are the cube roots of 1, okay? So for example, if you were to cube this number, you would get 1. So for example, if you were to plot this number on the complex plane, for example, so if you were to plot 1 plus I root 3 over 2 on the complex plane, where would it be? So you would get a, so the x-coordinate would be 1/2, and this would be root 3 over 2. So notice that 1 plus I root 3 over 2 is over here. At the tip, so this is a 30, 60, 90 triangle, right? So this is 60 degrees, this is 30 degrees, this is 90 degrees, right? So what does that tell you? So if you were to, and then 1 minus I root 3 over 2. So hold on a sec. Are these, hold on, oh, this isn't right. Oh, yeah. I'm sorry. The roots would be negative of these. I just need to throw in a negative here. Okay, my bad. But now if you were to draw these in the complex plane, they would look like this. You would go negative 1 plus I root 3 over 2 would be over here, right? Negative 1 minus I root 3 over 2 would be down here, right? You notice that the length of yes, exactly, these are roots of unity. So you notice that the length of these complex numbers is both 1, and the argument of this complex number is 120 degrees. The argument of this other complex number is 240 degrees, which means if you cube either of them, you will get 1. And so you actually get the following really kind of shocking factorization, like so. So essentially what happens here is that a cubed minus b cubed, what am I doing? I'm doing a cubed plus b cubed plus c cubed minus 3abc is actually equal to the following: a plus b plus c times a plus b omega plus c omega squared times a plus b omega squared plus c omega, where omega is a primitive third root of unity. So omega is like a negative 1 plus root 3i over 2. How cool is that? So this factorization is very, very beautiful, I think, and also quite powerful. Okay, so now I've shown you all of the different ways to kind of factor this expression, right? So there's this way, which I just mentioned. The first way that I mentioned was this. It was a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca. So we proved that using determinants. And then the second way we factored this is a plus b plus c times 1/2 times a minus b squared plus b minus c squared plus c minus a squared. A lot of interesting factorizations that live inside this particular expression. So let's actually use this to solve some problems. So as you can see, you can use this to generate a lot of tricky problems that you can use to kind of you know, if you're designing like a math Olympiad or something like that, this would be a fantastic identity to use. Okay, so we've already solved this one very quickly. Let's do a couple more problems. And once again, if you want to see the source of these problems, I put it up at the beginning of the video, so you'd have to rewind and look back if you're just joining. But let's do a couple more problems. So this one's a fantastic one. Let's take a look at this. By the way, I have not done these before, so it'd be fun. I thought it'd be fun to just do them together. So, though I have done one like it before, so I do have a very strong sense of what's going to happen. Okay, so here's a problem, a rather shocking problem, a problem that I think personally I would find very surprising. Prove that the cube root of 2 plus root 5 plus the cube root of 2 minus root 5 is a rational number. Okay, how might you do this? Okay, it's an odd problem. Okay, so how would you prove that this is a rational number? Okay, so based on the tools I've given you, it should be possible to do such a thing. But I think on its face, this is a very surprising fact, I think. Let's talk about how one might prove a statement like this using the factorization that we've given here. So let's see. Well, I know for a fact, because of the section of the book that these came from, that I know what I know I have to use the factorization that I've given you. So let's see what happens. If you set x equal to the cube root of 2 plus root 5 plus the cube root of 2 minus root 5, right? Then x minus the cube root of 2 plus root 5 minus the cube root of 2 minus root 5 is equal to 0, right? And remember, if a plus b plus c is 0, so if a plus b plus c is 0, then in fact a cubed plus b cubed plus c cubed is equal to 3abc, right? So let's use that now. So what this is telling me is that, in fact, x minus 2 plus root 5, right, minus 2 minus root 5 is equal to essentially 3 times the cube root of 2 plus root 5 times 2 minus root 5. You see that? Okay, so this is good. This is good news. So the root 5s are going to cancel. So basically we get that x, let's see, what's going to happen here? So, oh, I'm sorry, this should have been an x cubed, not an x. So x cubed, right? Also, there should be an x here, I think. So, right, a cubed plus b cubed plus c cubed is equal to 3abc. So that means that this cube plus this cube plus this cubed. So no cube here. So a plus b plus c being 0 means a cubed plus b cubed plus c cubed is equal to 3abc. Okay, now I'm good now. All right, so x cubed minus 4, right, is equal to 3x times the cube root of this expression. So 2 plus root 5 times 2 minus root 5 is just going to be 4 minus 5, so the cube root of -1, so you get negative 3x. Okay? So basically what this is telling me is that x cubed plus 3x minus 4 is equal to 0. Okay, that's very interesting. So if x is equal to this expression, right, then using this very amazing factorization fact that we've been going over, right, you immediately get that such an x must be a solution to this equation. Okay. Now, usually factorizing cubics is hard, but using the rational root theorem, you can check that 1 is a possible root, and in fact 1 is a root. So if you just plug in 1, of course, you get 1 plus 3 minus 4 is equal to 0. So 1 is a root. So if you factor this, this will be x minus 1 times something, right? Now we can use a synthetic division to figure out what the other piece is going to be. So we can put a 1 here. So this is 1, 0, 3, negative 4. So 1 plus 1 is 1, 0 plus 1 is 1. 1 times 1 is, wait a second, what am I doing wrong? 1 times 1, oh no, that's fine. So 3 plus 1 is 4, 4, 0. So the quadratic in here is going to be x squared plus x minus 4, right? Plus 4. So far, so good? Okay, what are the roots of x squared plus x plus 4? Well, if you look at the discriminant of this quadratic, negative b, b squared minus 4ac is going to be negative. So this quadratic only has complex roots. So this thing has complex roots. So it has non-real roots, I should say. So the only real root of this polynomial is in fact 1. 1 is the only real root of this polynomial. So if x is a real number, in fact, it has to be 1. So this is even more shocking than the problem originally claimed. In fact, the cube root of 2 plus root 5 plus the cube root of 2 minus root 5 is in fact equal to 1. Come on, who saw that one coming? That's pretty amazing, right? So 1 is equal to the cube root of 2 plus root 5 plus the cube root of 2 minus root 5. It's interesting, right? So let me know if there are any questions about that, and we'll keep doing more weird problems, more weird like Olympiad style problems that arise from this sort of thing. So yeah, the book is full of exercises. So let's see here. I'm just gonna pick one, and we can go for it. So here's an interesting one. I haven't done all of these, by the way, but we'll just see what happens. The book has solutions too, so if I can't figure it out, we can just look in the back. So let's do this one. A, B, and C are distinct real numbers. Prove that the following equality cannot hold. So how are we going to do this one? How are we going to figure out, how are we going to show that the following equality cannot hold? I'm sure everyone's already thinking about it. So we already know that the magic fact that we have on our hands is we already know that if 3 things add to 0, then their cubes add to 3 times their product, right? Of course, A minus B and B minus C and C minus A, in fact, most certainly add to 0, right? Of course, A minus B plus B minus C plus, well, hold on now. Even though they add to 0, their cube roots do not add to 0, right? So how are we going to use our, oh, what am I doing? Just these 3 things add to 0, right? So they're telling us that these 3 things add to 0. So their cubes need to add to 3abc. So of course, we know immediately that A minus B plus B minus C, which is the cubes of these 3, plus C minus A, is going to equal 3 times the cube root of A minus B, B minus C, times C minus A. Right? Okay. So, but then this is 0. The left-hand side is just 0. Right? So this is, in fact, just equal to 0, which means that one of A, and what A has to equal B, B has to equal C, or C has to, you had to check the previous result using a calculator for my sanity. I know, it's crazy, right? Like, I was not expecting that to happen at all, but it did. Also, since I know you're a fan of Mythologer, he had this video on why they don't teach the cubic formula in schools. right? I don't know. I know you've seen all of Mythologer's videos, Muhammad, but you know, he had this video about why they don't teach the cubic formula in schools, and let me tell you, that's one of the reasons why, is that expressions involving cube roots do not behave as you might want them to, or as you might expect them to, right? Okay, so in any case, this is telling us that 0 is equal to the 3 times the cube root of a minus b minus c minus a, which means that a has to equal b has to equal c, or c has to equal a. But they told us at the start that a, b, and c are distinct real numbers, which is a contradiction, right? So this one was not so bad. This one was not so bad at all. Let's see if I can find like a different one to do together using this magic factorization, as it's being called. Let's see here. Oh, this one's interesting. A little bit of geometry. Let's see here. Okay. Find the locus of points x, y for which x cubed plus y cubed plus 3xy is equal to 1. Okay, this should already be looking very, very familiar to you guys. What do you think the locus is going to be? I'm going to wait just like 30 seconds because I feel like this should be eminently doable given everything we have discussed so far. Okay, well, he has a video about why they don't teach the cubic formula in schools. So he derives the cubic formula. He does like Cardano's results and like all of that stuff. And one of the reasons he gives is that, you know, cubic formula can result in an answer, which is just something very simple, but it's very challenging to see that it is as simple as you might think it is. Okay, but in any case, we want to find the locus of points x, y for which this. In other words, we want to just find all solutions to this equation. So I'm going to do it now. I can already see it, right? So basically, here we have x cubed, right, plus y cubed minus 1 is equal to minus 3xy. Agreed? But we know that x cubed plus y cubed minus 1 minus 3xy is going to factor using our magic factorization, right? This is going to factor as x plus y minus 1, taking cube roots, right, times 1/2 times, I guess it would be like x plus 1 squared plus y plus 1 squared plus x minus y squared. Okay? So, but we know that, also this should be a plus. So we know that this, this left-hand side is equal to 0, which means that the right-hand side is equal to 0, which means one piece of the product on the right-hand side must be 0, okay? So this is basically telling me that x plus y minus 1 is equal to 0, right? Or this expression is equal to 0. We can ignore the 1/2. This expression is equal to 0. One of the two things must be true, right? So that's our locus. So x plus y equals 1 is going to be one piece of the set of all solutions to this equation. And this one, so the only way that the sum of squares can equal 0 is if they're all equal to 0. So in other words, this is basically telling us that to be a solution to this, x has to equal y, and x and y have to both equal -1. So the locus is, so sort of to draw the locus here, so drawing all solutions to this set of equations, it's just going to be x plus y equals 1, which is going to be like a, like a diagonal line here, right? And also the point -1 comma -1 is going to be this another solution here. So this is going to be the set of all solutions to this particular equation. Okay. Let me know if that makes sense. Let me know if there are any questions about this, and then we'll do a couple more problems using this wonderful identity. Okay. Let's see. There's some harder problems in the back too. I want to do something that I want to do something. Well, let's just go in order. Let's see here. Here's one. And yeah, feel free to chime in. I haven't looked at these, so you may well solve them before me. So the only piece of information I have that you also have is that you need to use the identity, right? So let n be a positive integer. Prove that the number 3 to the 3n times 3 to the 3n plus 1 plus 3 to the 3n plus 1 minus 1 is not a prime. Huh. Okay. So let's see. I don't know about this one. Let me see. So this is going to be like 9 to the 3 to the n plus 3 to the 3n plus 3 to the 3n plus 1 minus 1. Okay. Isn't the expression an even number? What a good... let me think about that. So, all powers of 3, so this is odd times an even, so that's going to be even. Even plus odd. Is it even? That's actually not a bad approach, Vave. Good call. So I guess you would have to show that it could never equal 2, but I guess it'll very quickly outpace 2. Does that actually work? No, I mean, not bad. Good work. So yeah, 3 to any power. So this is odd, right? This is even. And this is, again, odd, right? So odd times even is even. Even plus odd is odd. Wow, that works. Good work. Good work, man. Good work. That's tight. I really like that. That's so much better. You know what? I'm not even going to do the other solution because that was awesome. That was just a better answer. Good work. Let's see. I love that. Good work. So let's do the next one. So, all right, let's find like a really hard one. All right, I'm looking for like something like near the end, you know, just kind of brutal. So, how about this one? All right. Let me know if you can see it, and let's give it a go. Let's give it a go together. So, a cubed plus b cubed plus c cubed plus 3abc over 2 is greater than or equal to the largest of a, b, and c if a, b, and c are the side lengths of a triangle. And yeah, if any of you have any other bright ideas, please let me know. So, let's see here. Well, you know what? We can assume without loss of generality that like A is the largest one, right? So assume without loss of generality that the maximum of A, B, and C is just A, right? So now we're trying to show that, the cube root of A cubed plus B cubed plus C cubed plus 3ABC over 2 is in fact just greater than or equal to A, right? Let's see here. How are we going to do this? Well, we can cube both sides, right? And then we would get, then we would be just, and cubing is monotone, so that's safe. So we would have A cubed plus B cubed plus C cubed plus 3ABC over 2 greater than or equal to A cubed. So this is 2A cubed, right? So this just becomes a negative. This is greater than or equal to 0. Okay, this is good. This is good. Of course, we can do our magic factorization again. So let me just do that real quick. So we're trying to show that this thing, right? We're trying to now, we've reduced it down to this thing, okay? So what else? So this is going to be, so this is like B plus C minus A, right? 1/2. There it is. We're done. Because the second half of this factorization is always positive, right? You see that? So this is 1/2, it's like A minus B squared plus B minus C squared plus C minus A squared, right? So this is just the sum of the squares of positive numbers. So essentially, all we need to show, this is actually just, all you need to show is that B plus C is greater than or equal to A, which is just the fact that the sum of two sides of a triangle are greater than or equal to the third side of the triangle. So that's how you do this one, using the magic factorization. That was fun. Let me know if there are any questions about that. Okay, I can do one more. Why not? Let's see. They are getting worse, though, I feel like. Okay, yeah, this one seems rough. Let's take a look. Oh, let me shrink it. I don't want it going over my, orange line. Okay, hopefully you guys can see that one. All right, so A, B, and C are distinct positive integers. Let K be a positive integer such that AB plus BC plus CA is greater than or equal to 3K squared minus 1. You want to prove this. Okay, well, pretty clear of what okay, so you start with the expression. So it suffices to show that A cubed plus B cubed plus C cubed minus 3ABC is in fact greater than or equal to 9K, right? Okay, so it suffices to show this identity, but of course this you can factor as usual. And I'll choose to write the factorization like this. So this is A plus B plus C times, A squared plus B squared plus C squared minus AB minus BC minus CA. So, of course, this is going to be greater than or equal to, I guess, A plus B plus C times A squared plus B squared plus C squared minus 3k squared plus 1. But why would that show that the original expression is bigger than 9k? I'm not sure how to finish this one. Let's see. So a plus b plus c. I'm open to any ideas if anyone has any. Let's see. So this is positive. Why is this bigger than 9k? I don't know. Let's see. Am I being silly in some capacity? I don't know. Maybe something involving arithmetic mean, geometric mean. Maybe. I think, yeah, I know it's fine. I actually think this factorization is it's equivalent to, not equivalent to, but you can prove AMGM using this particular factorization. Let's see, try dividing a plus b plus c. I'm not sure I see if that would help. We didn't use that they're distinct. We didn't use that they're distinct. You know, if they're... We didn't use that they're distinct. So... I don't know. So... You can also factor this as... Instead of writing the second term like this, you can also write the second term as like 1/2 a minus b squared, right? Plus b minus c squared plus c minus a squared, right? But if they're all distinct, each of these are at least 1, right? So if each of these are at least 1, yeah, I think there's something here because if you look at, maybe someone can help me out here. So if you look at this expression, right? If a and b and c are different, then this is the square of the distance from a to b and the distance from b to c and the distance from c to a, right? Which are all at least 1. Can we do better than that? So yeah, this thing is equal to this thing. Yeah, 3/2. Can we do better than that? I don't know. Okay, I don't want you guys just like staring at me. I'm gonna look up the solution. And then, hold on, it's in this textbook. I just need to find it. let's see, it's problem 1.13. Yeah, if it was me alone, I'd just sit here for hours thinking about it. But, you know, I got a stream to run. So let's see here. Okay, here's the solution. Okay, so I'm just paste this in. Okay, I'm just gonna put this up here. So then there's more solution. Let's see. Okay, so there it is, divided into two pieces is the solution to this problem. So the 3/2 wasn't good enough, it looks like. You needed, that's embarrassing. So you can do better than 3/2 because if you think about three different numbers on, if you think about three different integers on the number line, then two of them have to be at least 2 apart. So the best you can do is not 3/2. The best you can do is 3. Do you see that? So if you look at A, B, and C, then at least one pair of A, B, and C must be at least 2 apart, right? So that tells you that this thing is, so this quantity is at least 3. So that tells you that this quantity is at least 3A plus B plus C. So all you really need to show is that, yeah, so if you can show that 3 times A plus B plus C is greater than or equal to 9K, which is the same as showing that A plus B plus C is greater than or equal to 3K, right? And, okay. And then you can square both sides and you're done. Oh, well. Yeah, I completely missed that one. Darn. But anyways, hopefully it makes sense. Let's see. All right, let's, okay, well, we're running out of time, but let me, see what else we can do here. Maybe one more for old time's sake. Let's see. Maybe I should pick like a really hard one or like a not as hard one. I don't think that one was so hard. I just should have thought about it for a second longer. Let's see here. How about this one? Let A, B, and C be rational numbers such that coffin problem? Yeah, I know. Wait, is that a coffin problem? Actually, that'd be really interesting if that were true. Do you know IHTFY, if that is actually a coffin problem? Because that'd be really interesting if it were true. Okay, let's take a crack at this. Let A, B, and C be rational numbers such that A plus the B times the cube root of 2 plus C times the cube root. Okay, come on. Okay, this one isn't so bad. So I feel like some of these could make for good coffin problems, actually. If you guys don't know, well, I don't know. Maybe I won't get into it here, but coffin problems are problems with a rather sordid history. You can look them up. It's kind of interesting. So so they're problems that are really, really hard, but have very easy solutions. And you can use them for discriminatory purposes because you can give a student you don't like such a problem. And then if they complain, you just say, oh, but the solution was so easy, you know? And they were used for, unfortunately, that's right. That's right. All right, let's see. In any case, putting that aside, let's try this problem. So using the magic factorization, we know that, for example, a cubed plus 2b cubed plus, I guess, 4c cubed is going to equal 6 ABC, right? So that worked out pretty well. So a cubed plus 2b cubed plus 4c cubed is equal to 6 ABC. Okay, now we need to use this to prove that a equals b equals c equals 0. So one thing to keep in mind is that a, b, and c are rational numbers. So I think we can assume a, b, and c are integers by clearing out the denominator. So I'm just going to say assume a, b, and c are integers by clearing out denominators, right? Okay, so assume a, b, and c are integers by clearing out denominators. Okay, so now we have this thing. Maybe there's like a good parity argument here to be made. I'm not sure. Let me think. So you want to show that the only way that this equation could hold is if a, b, and c are equal to 0. Not sure. What do I do here? So a cubed plus 2b cubed plus 4c cubed is equal to 6 abc. So can we do here? Yeah, I'm not sure. Is it a good idea to think about this maybe mod 3? I don't know. Okay, I'm not sure. I'm pretty sure this is going to be... So if we work mod should the right side have radicals? No, because if you multiply the cube root of 2 with the cube root of 4, you get the cube root of 8, which is 2. So I do not believe that the right-hand side needs radicals. Though, actually, okay, so So here we go. So you can reduce mod 2, right? And then you get that a cubed is actually congruent to 0 mod 2, which means that a is congruent to 0 mod 2. Right? So a is even. What about b and c? Do b and c have to be even too? Because that would be a contradiction if it were true. So a is even, right? So if a is even, does that mean is be necessarily even? Well, okay, A is even, so you can write it as like 2x or something. But if you do that, then you would get that. Right, so if A is even, you can write A as 2x. So that means like 8x cubed plus 2b cubed plus 4c cubed equals 6abc, right? But then you can cancel out 2's, and then you get that 4x cubed plus b cubed plus 2c cubed is equal to 3abc, which of course tells you that now you reduce again mod 2, and then you get that b is even as well. So A is even and B is even. Right, but then you can... Okay, so A is even and B is even. But does that mean that... Okay, let's see here. Right, but then same energy, C will also have to be even. So if you make A 2x, B 2y, right? Then you would get like 8x cubed plus 16y cubed plus 4c cubed is equal to 6 times 2 is 12, so 24xyc, right? Then you cancel out all the 4's, and you would get that 2x cubed plus 4y cubed plus c cubed is equal to 6xyc, which tells you that c is also even. But that means you didn't clear... Like, this is a problem because you can clear denominators in a way where A, B, and C are not all even. So I don't know, it's kind of an ugly thing, but... So that actually does it for you. So that gives you a contradiction, right? Because you can clear out denominators in a way so that at least one of them would be odd, right? Because you can keep canceling, right? If they're all even, you can divide both sides of the equation by another 2. So you can keep dividing over and over again, right? And that actually does it. I actually think that does it. That's a valid solution to this problem. All right. I think I'm going to call it here. Thank you so much to all of you who came out and joined. Hope you enjoyed the music. Hope you enjoyed the problems. I'll be out here again on Saturday doing more stuff. And I think that is it out of me. So thank you so much once more. And